Okay, so in the second part of this lecture, we're going to wrap up a couple more ideas and concepts related to the real Mosfet threshold voltage. And one of the things we're going to start to do is to introduce PMOS devices as well. If we're going to make an inverter, we need both NMOS and PMOS, and they call that, right, the term for those together is CMOS, complementary metal oxide semiconductor. If you don't have CMOS, meaning both N and PMOS, you can't make effective logic circuits. So we better focus our attention a little bit on PMOS too to understand its threshold voltage as well. So here's NMOS, right? P-type substrate, make an N-type channel, you get your current flow between source to drain. Here's PMOS. I have an N-type region underneath here, and I apply a negative voltage to the gate to create negative charge here, positive here, which gives me a P-type channel to connect my P-type source and drain. Now you'll notice here that I have N-type here and a P-type substrate underneath. So why do I have that? Why does PMOS need this more complicated structure where I've got semiconductor regions here and here, but also another one out here, where this one only had two, right? Well, think about that. If I need to have complementary metal oxide semiconductor circuitry, I need to have both the NMOS and the PMOS on the same substrate. Well, look, same substrate, right? And so you could see I set the doping level here to be ideal for NMOS. So it's set to a P level doping that's ideal for NMOS. And then here I diffuse in phosphorus atoms to create my N-type area, which I can then invert to my P-type channel. So this allows me to integrate both of them on the same substrate. Okay? So, key question then is, for our threshold voltage for PMOS, how does switching the doping level here from P-type to N-type, how does changing the doping level affect my threshold voltage equation? Does it shift or flip my voltage or nothing? Well, here's my threshold voltage equation. The term out here shifts, okay? Because for both of these, I'm using the same gate material. I'm using N plus polysilicon, okay? And so if phi sub m stays the same, phi sub s just becomes larger or smaller. Remember that previous plot we showed for phi sub ms as a function of doping? As you change doping levels, you shift the Fermi level, right, for the semiconductor, and so that shifts this in magnitude. Okay? Look at the next term, Q sub I over C sub I. Well, Q sub I was that oxide fixed charge. The oxide has nothing to do with the semiconductor underneath it, right? And the capacitance C has nothing to do with the semiconductor doping underneath it. So this has no effect in terms of how we change it for the threshold voltage equation. Now let's look at these terms here. How do these change? Well, QD over CI will instead transform to not QD, but it will transform into QA over CI, and it will now have a net positive sign because I can keep it in the equation like this, okay? But remember, C doesn't change. QD is depletion for, I'm sorry, I'm going to go back here. This is, ignore this, QA, okay? The QD, I was thinking of donors versus acceptors. QD is just for depletion, okay? Now, let me step back and try this one more time here, okay? In the case of a NMOS device here, QD is going to be boron atoms, which have a negative charge, right? So a negative and a negative gives me a net positive. In the case of a PMOS device, I'm going to have donor atoms, okay, which are phosphorus. Phosphorus donates an electron to the silicon. When it donates that electron, it becomes positively charged. And so these depleted charges, as we get depletion for this, okay, this will have a positive charge. So I get a positive and a negative. The net term here is negative. Before, the net term was positive. Now it's negative, so this switches signs when you do PMOS. Just trust yourself in terms of what is the depletion charge itself, and just put it in this exact same equation, and you'll find that it counteracts this negative symbol or it doesn't. Okay. The last one is 2 phi sub f. Does this one change? Well, think about this. Okay. If I have a semiconductor, and here's the intrinsic Fermi level. Okay. For NMOS, like I have here, I'm starting with the Fermi level down here. It needs to shift in this direction, right? Well, for PMOS, I have N-type material. My Fermi level is up here. It needs to shift in this direction. So this will be in the opposite direction because phi sub f for NMOS will be up here, right? So it's on the opposite side of the intrinsic level. And so this will become a negative as well. That should make sense because if you think of this PMOS device here, I need negative voltage on this side, negative charge to get positive charge in the channel, right? Does that make sense in terms of these contributions? Well, positive Q into here means a negative voltage. This is now negative as well. And so this is a net negative, meaning my threshold voltage for a PMOS device is negative. You have to apply negative voltage with respect to the substrate to get the positive charge in channel to form. So that should make sense. Here's a plot here of the threshold voltage versus doping level. So this is either doping level in a P channel or an N channel device. Let's look at the N channel device first here. That's the one we're most familiar with, NMOS device. Okay. And so you can see that at low doping levels here, okay, if you add in all these effects, the device is actually on at 0 volts. How could this be? Well, what this clearly shows you, okay, is that the effects which reduce your threshold voltage, phi sub ms and q sub I, must have a pretty powerful effect that they make the device be on even at 0 volts. And so when you put this in a logic circuit, you're going to have to offset it with a DC voltage somehow on the logic circuit in order to have these things act like logic switches. So that's not critical, but just wanted to explain that to you. You can see that as you increase doping level, the threshold voltage starts to increase. And so what that tells me is that these things, which increase your required amount of voltage, remember, this is the price we have to pay, must dominate over this, because we said that this became more negative as you increased your doping level in the substrate. These ones must dominate because they're positive and they increase as you increase doping level. More atoms to uncover, more Fermi level shift that's necessary. And so you can see your threshold voltage is increasing, so these terms must dominate over this in terms of the effect of increasing doping. Here's a P-channel device. For a P-channel device, we need negative voltage to turn it on, right? So anytime you apply a voltage below this curve, the device will be on, right? And so you can see the exact opposite effect. As you increase your doping levels, these terms for the PMOS device, you must have to pay more negative voltage, increasing amount of negative voltage to turn it on and to get current flow between the source and the drain. So let's look at our current voltage characteristics for these devices just to make sure we set these things up correctly. So here's NMOS. Let's assume it's N channel, okay, and enhancement mode. So I've got P-type substrate. Here's my N-type channel, hence why it's called NMOS. And I know if I want to get drain current versus drain voltage, I need to apply positive voltage to turn this device on. So you can see my threshold voltage for this example device was around 3 volts. And of course, as I increase my drain voltage, I get a linear region at first, but then I run into saturation as the voltage I apply here, or the voltage I apply here on the drain, this positive voltage cancels out this positive voltage, so the channel will pinch off. So in this case of this device here, the channel would kind of pinch off like this, right? So there's my negative charges in there, because the positive voltage here would cancel out the positive voltage here, and you don't get the net voltage drop you need right here to fully invert the channel there. If you look at a PMOS device, how are we going to operate that? Well, we know that we're going to apply a negative gate voltage, okay, to get a positive channel. And notice how I set this up. Now I put a negative drain voltage on here. You'll see why that's going to be important in a second, okay? That's going to be critically important when we start to build logic circuits up. But I'll put a negative drain voltage. Well, that automatically puts me down here in quadrant 3, right? And if you look at my source to drain current, now I'm going in the opposite direction. Here I had positive voltage on the drain, so current went from drain to source. In this case, I put negative voltage, meaning that my net current will be in the opposite direction. So my drain current is also negative. So negative drain voltage, negative drain current. That puts me in quadrant 3. More and more negative voltage. I get more inversion of the channel. I get more holes here to conduct, and I get more and more current flow. And I have the same effects of having a linear approach, linear increase in current with small Vd, because this is just like a slab of semiconductor. It's like a conductor, so it's V equals IR. So I get this linear response. And then eventually, the negative voltage I apply here starts to cancel out the negative voltage on the gate right here. No net voltage drop. And then you run into saturation for all these curves as well. I want to note there is one mistake here. I noticed that if I look at my depletion region here, if this is negative here, negative side on a PN junction is negative voltage on a PN junction on the P side is reverse bias, right? Well, my depletion region should be thicker here and thinner here, so I just drew my thicknesses of my depletion region opposite here. We'll talk more about that in a second, though. So let's do an inverter, and you'll see how this all fits together, quite nicely. So from earlier coursework, you know that inverters, buffers, repeaters, which are repeaters, and, or, NAND, NOR, all these logic gates use complementary metal oxide semiconductor devices, meaning they have both NMOS and PMOS devices together on the same substrate. You could draw an inverter like this, right? The input voltage will be inverted when it comes out the other side to the output voltage. You could do a little table like this where if I had 0 volts in, it gives me 5 volts out. If I have 5 volts in, it gives me 0 volts out. And you could also draw it like this with NMOS and PMOS devices in a simple logic circuit here. Here's my input voltage. Let's say I have, let's start with the case of 0 volts in. So 0 volts in, what would I get? Well, 0 volts will not turn on the NMOS device, right? And so 0 volts is no voltage on the NMOS device. Then I basically will see that I get this is not on. 0 volts will turn this on. So if VDD is 5 volts, I get 5 volts to go to the output. So 0 volts was inverted to 5 volts at the output. If I put 5 volts in instead, 5 volts won't turn on the PMOS device. 5 volts will turn on this device, which connects the output circuit to ground, and so I get 0 volts out. So 5 volts turn to 0 volts. If you want to see how this works, I'll show you on the next slide. You'll see how this device here works beautifully at doing exactly what I described here. So, skipping the previous slide because it's not that critical, let's get straight to this inverter here. So I'm going to assume the ideal case to keep this simple, okay? So you can understand this the simplest. And what I want you to do is I want you to notice how the source biases beyond the semiconductor, beyond the source, but not the adjacent FET. So we'll talk about that in a second, okay? And so let's set this up here. I'm doing an inverter where I'm going to go from 0 volts to VDD. We'll assume maybe VDD is 5 volts. So I'll label these. I'm going to go ahead and label these now as 5 volts. I'll say VDD is 5 volts and VDD down here is 5 volts. And that means if Vout is VDD is 5 volts, then that's going to be 5 volts, and that's going to be 5 volts. Oh, sorry. That's going to be 5 volts here. Okay? So, the first thing you have to do is find some place to start. Okay? And the one challenge you see here is that for both the NMOS and the PMOS devices, how can I tell what the voltage drop is across here if I don't know the voltage down here? Notice that there is no power sources connected to the substrate. And so previously, when we talked about turning a device on or off, we talked about applying a voltage with respect to the layers underneath the gate. But if we don't have a voltage source out here, how can we possibly begin to know what the voltage drop is across here, positive or negative, and determine whether or not it's going to make a channel or not? Well, we've got to start somewhere, and so here's where we'll start. The first thing I want you to note here is that my source here for the NMOS device is grounded. So I can write 0 volts here. So let me get my pen out, and I will write 0 volts here. Now, I want you to note that right here I have a PN junction. This is very important, okay? If I have only two options, 5 volts and 0 volts, then I know out here it could never be less than 0 volts, right? So I know that out here, if I've only got two voltages applied to this thing, 0, 0, or 5, then the voltage here has to be somewhere between 0 and 5, because that's all I'm applying anywhere on this device, right? Okay. Well, if this is between 0 and 5, what could it be? Well, if this is 0, as soon as the voltage out here would ever try to become greater than 0, it would forward bias this PN junction, and that voltage would be brought down to 0. So I know that the voltage out here for here and here is 0 volts, because anything greater than 0 volts would forward bias this PN junction. And so basically, this PN junction here pulls the region out here down to 0 volts. 0 volts here as well. So I put a 0 there and a 0 there. Okay? So we're moving along here. Now let's, I'll put a 0 here too. Let me draw a 0 in here. So I've got 0 in there. Okay? Now let's go over to the PMOS side of this device. Well, I know I've got 5 volts at the source of this, so I'll put 5 volts here. Same question here. I've got an N-type region here. Here's my N-type region. It can only be between 0 and 5 volts, right? That's all I'm applying to this is 0 and 5 volts. So what would the N-type region be? Well, what if the N-type region here became less than 5 volts? Wouldn't this PN junction also forward bias? And so that forward bias on this PN junction will set this equal to 5 volts. So I'll put 5 volts in here. So I know that the N-type region here is also 5 volts because it can never be less than 5 volts, because if it became less than 5 volts, it would forward bias this PN junction. I'd get current flow, and that would bring it up to 5 volts. But then you're like, oh, wait a second. There's a problem here. If I've got 5 volts here, what about the 0 out here? Aren't those in conflict? They're not. Look. Positive voltage on the N side of a PN junction is reverse bias. So I've got 0 volts on the P side, 5 volts on the N side. It's reverse bias. And so these voltages don't interfere with each other because this diode's reverse bias. So I don't have to worry about this 5 volts giving me a lot of current flow in between here. So this worked out beautifully so far. I can see that my voltages for one device don't interfere with voltages on the other side. Okay? Now, let's keep moving along here. And let's look at the output now. So, if I want to know my output, I want to know which of these devices is going to be on. Is the NMOS device going to be on, or is the PMOS going to be on? The device that's going to be on is going to take its source voltage and take it out the drain. So is it going to be the 5 volts that makes it out, or the 0 volts that makes it out? Well, you can see I've already drawn this with the answer here, but let's investigate it anyway, okay? So, at my gate, you know I've got 0 volts, right? Because my input was 0 volts. Well, if I've got 0 volts here and 0 volts here, my net voltage drop across my oxide is 0 volts. Well, of course, if I've got no voltage on an ideal MOSFET, then it's not going to turn on, right? If I have no voltage across here, I get no charge here, and if I have no net charge here, how could I create these electrons I need to get conductivity through here? So I know this device is turned off, and then this 0 volts does not make it here to the output. Let's look at this side here. I've got 5 volts here, and I've got 0 volts here. How do I handle that? Well, here's how I like to handle it. It's a capacitor, right? So let's say I've got on one side of the capacitor, I've got 5 volts down in the P-type region, and I've got 0 volts at the input. Okay? Well, isn't that the exact same thing in terms of voltage drop of having 0 volts out on this side and minus 5 volts here? Because in both of these, I still have the same net voltage drop. All I did was I subtracted 5 from both sides here, 5, and I get minus 5 and 0. So subtract 5, I get the same net voltage drop. And that helps me understand this, because if I have minus 5 volts here, negative voltage, negative charge with respect to this side, I get positive charge on this side. Yep, that makes sense because I need to build up a p-type channel. So again, I have my 5 volts here, which I had figured out before because it's p-n junction forward biases. So here's my 5 volts, here's my 0 volts. 0 and 5, I said, is the same as minus 5 and 0. Okay, if that's the case, and I've got minus 5 effectively here, and that's a negative charge, then I get positive charge here. I know it turns this on because I want positive holes here to get a conductive channel here. So then my 5 volts makes it through to here. I can label my voltages, 5 volts. I know I've got 5 volts at the output because this is an inverter. So my 0 volts inverts into 5 volts at the output. And I can label this as 5 volts here. And what about the 5 volts here? Do I have to worry about it screwing up over here? Nope, 5 volts, 0 volts, reverse bias diode. Beautiful. So everywhere I had to worry about having a net current flow through this device, I ended up with the reverse bias diode. And that means when this device latches to a particular logic state, for example, inverting 0 volts to 5 volts, I get no net current flow through any of these junctions, which is perfect because I don't want my MOSFET to consume electrical power. So you can see this worked out very well. Okay? Let's do the opposite case next now. Let's do an input of 5 volts and have it invert to 0 volts. So it's the same setup out here. We have the same cases we had before, where if I've got 0 here, I know I've got 0 here, and that means I've got 0 here, and I said I've got 5 here, which means I've got 5 here. Okay? Let's figure out the rest. Well, if I've got 5 volts at the input, and I've got 5 volts here, I got no net voltage drop across this gate here. Well, if I've got no net voltage drop, then I get no charge, right? No voltage drop across a capacitor, no charge. If there's no charge, then of course I've got no net charge here. I get no p-type channel to form. And remember, out here, yeah, you've got electrons, but for every electron, you've got a phosphorus atom. So the net charge is 0, which makes sense. Okay? And so that means this 5 volts can't make it to here. Let's look at the other side. If I've got 5 volts here and 0 volts down here, positive voltage on this side, positive charge, means negative charge has to show up on the other side. I get my n-type channel. The 0 volts makes it to the output. So I can label this here becomes 0 volts. I've got my 0 volts at the output. I've got my inverter. I get 0 volts here. Am I concerned about current flow here? Nope. 5 and 0, that's a reverse bias p-n junction. Again, it works beautifully. No power consumption. It's latched into the right logic state for now inverting 5 volts into 0 volts. If you notice these diagrams, the reverse bias depletion regions I made thicker. Okay, so you can see that there. And the other thing I want to note about this before we leave this slide is this shows you how you make MOSFETs. You basically take one substrate, and then the first thing I will do is I will diffuse in my N-type region over here and my P-type region here with the exact doping levels that I want to have my right threshold voltages and good MOSFET properties. Then over here, for the NMOS device, what I'll do is I'll diffuse in my drain and my source. So I'll diffuse in dopant levels to create that. And then over here, I will diffuse in additionally my drain and source with P-type material. And then all I have to do is modulate the channels to be conductive or not for these cases and get the action I can see here. So again, I can't emphasize enough how beautiful it is that a semiconductor system works so well that you can make a device so simply, integrate complementary metal oxide logic. And the thing I love about this is the thing I said at the beginning of the course. This whole course is based on p-n junctions. And you can see it here. You can see that an inverter is heavily dependent on PN junctions, especially if it's going to latch between logic states and not have any net current flow to hold the logic state, which is what I want. I want a low power microprocessor. Let's finish up with a couple of the currents for MOSFETs. We talked this whole time about threshold voltages. I should give you some equations for current flow though. So it can be shown that, meaning I'm not going to derive it, that at low drain voltage, meaning not in saturation, when you are in your linear regime, okay, where this is just acting like a slab of conductor, V equals IR, more voltage, you get more current, that your current can be predicted as follows. And so you can see, yep, it's linear. If I increase gate voltage, I get more output current, okay? This term out front we'll get to in a second. This is our transconductance parameter. We'll get to that in a second, okay? But if you want to calculate this, you can see this L, that's the length of my channel. Z is the width of the channel into the plane here. So if you look at this being long into the screen, that's Z there. We'll get to mu sub n in a second. C sub I is my oxide capacitance. So if I want to make a really good MOSFET with fast switching times, okay, meaning low RC time constant, this equation tells you all the things you want to do to make a fast MOSFET. Well, I would love to have a shorter channel length. If I have a shorter channel length, I can get more current out, right? Smaller L, more current. That makes sense. Just make shorter channel length. I have less resistance here, so it's easier to get current flowing through the device, okay? I would also like to have a larger channel width, meaning wider into the plane here. Basically, if I look at this in terms of being a slab of conductor, the wider it is, the more cross-sectional area I have for current flow, that would help make this thing switch faster. I would like to have a thinner oxide layer. Higher capacitance, thinner oxide gives me higher capacitance, gives me more current. Why? Because a higher capacitance basically allows external voltage to turn into more charge. So again, you know, remember, Q equals CV, and Q is the amount of charge I have here down in this channel. And so if I have higher capacitance for a given voltage, I'll get more charge. More charge here means a more conductive channel, more current flow. So that should make sense. And I'd also like to have a lower threshold voltage because threshold voltage is fighting against my gate voltage, so that makes sense. The last thing I have here out front is this transconductance. It's called the surface mobility, mu sub n. So what is this surface mobility? Well, for silicon like this, for p-type silicon, I normally get 1300 from my mobility. But this surface mobility, so it's got a bar over top here, it's lower. Why does it get lower? And notice also that the surface mobility, as I increase my gate voltage, it gets worse. My mobility goes down as I put more gate voltage on that. Why is that? Well, here's why. Remember we said we have this interface charge here? This is basically where the oxide and the silicon match up. You've got two different material systems with two different types of bonding. And where they match up at the interface, you are bound to have silicon dioxide with an incomplete bond. You're bound to have silicon atoms that don't have 4 other silicon atoms to bond to at that interface. And anytime you have atoms without complete bonding, you always have dangling charges and a net charge of positive or negative. And so right at the surface here, you get these positive and negative charges. Well, imagine if I'm an electron trying to go from source to drain. So current flow in this direction is electrons going this way. If I'm an electron and I'm trying to go across here, then I'm going to be attracted or repelled by these charges. So, let's say I'm going along underneath the oxide, and there's a positive and a negative and a negative and a positive and a positive and a negative, okay? Look at the path the electron's going to take. It's trying to make it across there. It gets attracted, then it gets repelled, then it gets attracted, then it gets repelled. That's a pretty zigzaggy path, isn't it? The more zigzag it is for the electron, the easier it is for it to run into silicon atoms or other electrons. And so if you have more collisions because you're making it go more zigzaggy because of the electric field influence of these charges, then that decreases your mobility. And so I have a surface mobility, which I calculate, not a traditional mobility because of these interface charges here. Why does it go down as I basically increase my gate voltage? Well, remember, when I plotted my charge for a device like this, if I had my plot of charge, I had my depletion charge, and I had my inversion charge, where this is my distance into the device, and this was my charge, right? Well, this charge, as I increase my voltage, it increases mainly right at the surface, right? It increases exponentially at the surface, an exponential growth because of the Fermi level distribution in terms of how inversion charge grows. And so as you increase your gate voltage, more and more of your charge is right here against that interface because it's increasing exponentially. Therefore, more of the charge is basically experiencing a stronger influence of this interface charge. Furthermore, as I create more charge, it becomes like a crowded freeway, right? If I have more and more electrons zigzagging across here because of this, and the freeway gets more crowded, the flow of traffic slows, and yep, my mobility goes down. And so this all makes sense that as I increase my gate voltage, my mobility of the channel actually decreases. Fortunately, you get a lot more carriers, and so your net current flow goes up, but it doesn't go up as much as it could because the mobility is going down. Now, if you want to look at your current for all drain voltages, both the linear and saturation regimes, it can be shown that you can derive the following equation. I know this looks kind of messy, but it's not bad. You could plug it in. Once you've plugged it into Excel or some kind of MATLAB or other modeling tool, you can just use it as desired. Okay? And so it basically predicts both the linear region and the pinch-off saturation region as well. So it captures both of them, which is pretty nice. Okay? And again, you get saturation because the channel pinches off. I've applied so much positive voltage here, it cancels out with the positive voltage here. No net voltage drop, no channel. Here I've got 0 volts, positive voltage here. I got my maximum voltage drop. I've got my widest channel. And there's the pinch-off right there. Again, this term out front, K sub n, is the same. That's my transconductance parameter. We'll look at that more in a second. So, here's my drain current versus drain voltage for a couple different gate voltages here. More gate voltage, more current. This is for an NMOS device. In the linear regime, here is my equation. Okay? At saturation, I can simplify the equation from the previous slide down for saturation current to be the following. So here's how I can calculate saturation current. And notice, okay, that in VD sat, you're like, where was my effect of my gate voltage? Well, VD sat is just VG minus VT. And so this VD sat equation is calculated as VG minus VT. There is no effect of VD inside here, and that makes sense because when you're in saturation, you don't get an effect of VD. And so you just substitute in for VD here, VG minus VT, and that gives you your saturation current. The only way to increase your current once you're in saturation is to increase VG. Okay? Another important parameter for MOSFETs is their transconductance. Remember transconductance? Basically transferring an input voltage to an output current, and its conductance because it's I over V. Okay? So units of not resistance, but conductance, which is Siemens, amps per volt. And if I want to calculate that, it's easy. Just take the derivative of ID with respect to VG. So put this in for VD in here, and for VD sat. Take the derivative. Here it's VG minus VT squared, right? So this is, if I put this in here, it's VG minus VT squared. Take the derivative of that. I just get VG minus VT. I had a 1/2 out here in front. Well, when that squared term dropped out here in the 2, the 1/2 went away, and that's where I end up with my transconductance saturation being this equation here. Okay? You can look at this plot up here and say, well, what's my transconductance for this? It's pretty easy to calculate. I'll do an example of 4 milliamps and 2 milliamps, okay, divided by 2 volts minus 1 volt. So I change by 2 minus 1 to get a change in 4 and 2 milliamps, and I get a transconductance of 2 times 10 to the minus 3 mhos, or you could also call it Siemens. If you do MOSFET analysis, you're also going to look at something called the transfer characteristic, which is how much drain current versus gate voltage, okay? Look what's happening here. You get to the threshold voltage. I'm sorry, that should say VT here. So that should say VT. If you want to figure out what your threshold voltage is, you'll do the transfer characteristic, drain voltage versus gate voltage. You'll get this curve like this. And for the linear portion here, you'll draw a dotted line here like this. And where that intersects the x-axis here, that's how you record your threshold voltage for a given device. Now, I want to reinforce something. Notice here that the drain current is linearly dependent on gate voltage. Don't get confused. We said previously that inside a MOSFET, the electrons are generated exponentially with surface potential. Okay? That was the amount of band bending surface potential right under the gate oxide. However, surface potential is not externally applied gate bias. Our externally applied gate bias is just that of a classic capacitor. So I've got VG here, and then I've got a channel down here where when I apply my, so it looks like VB, that's supposed to be VG, sorry. I apply my gate voltage out here, then the charge appearing across my gate capacitor should be calculated according to Q equals CV. And if the amount of charge I have in my channel determines the conductivity of the channel, then I should see my drain current go up proportional with gate voltage. More gate voltage, more charge in the channel, more current flow because the channel is becoming more conductive. Okay? And if my transconductance is change in drain current over change in gate voltage, right? And it was on the previous, we showed this, it to be calculated to be this on the previous slide, well then that should be my slope here, right? And so my slope here is what I call my transconductance parameter. So you can see I get that same transconductance parameter I had in the equations before. You can see it show up right here. It's the slope of this line, and lo and behold, look, VG turning into current, right? VG turning into current. There's the slope. There's the slope, transconductance parameter. It should all make sense. Okay? Now, if I want to look at my transconductance versus gate voltage, for a MOSFET, you're going to see it goes up, reaches its maximum point, then it's going to go down. So here's where I'm getting my device ramped up in the normal mode. I'm getting my conductivity up. I get my maximum transconductance. Okay? As I create my channel, but then it starts to drop off. Why does my transconductance drop off as I go to further gate voltages? Well, there's two things that happen. Okay? First thing is, remember that surface mobility, that mu sub n? My mobility of my electrons in my channel actually goes down as I crowd it with more electrons and as they start to get going in a zigzag pattern because of that surface, that interface charge, so it goes down. The other thing that happens is eventually my source to drain series resistance kicks in as well. And so my transconductance goes down at some point. So there's always a sweet spot for a MOSFET where you get your maximum transconductance. Last topic, and then we're done with advanced MOSFETs, capacitance. And this should be easy. It's just going to be PN junctions. So remember, for PN junctions, you reverse bias a PN junction, depletion width grows, right? So if I reverse bias a PN junction, my capacitance goes down as I reverse bias it. If I forward bias it, my depletion region width gets smaller, and my capacitance will go up. Okay? So for a MOSFET, here's how my capacitance is going to map out as I put voltage on it. So here I'm applying voltage on this axis and measuring my capacitance here. So let's look at what we get here. So first off, let's go out to, this is for an NMOS device, let's go out to negative voltages on the gate. So negative voltages shifts things up, right? Negative voltage shifts up, and we said we get accumulation. So if I put more and more negative voltage, I just get more holes accumulating here, and I've got tons of electrons here because this is like a metal, right? And so my capacitance will be charges on either side of my oxide, and so I get no capacitance change with negative voltage. Here's 0, negative voltage. And so here I am in strong accumulation. The capacitance stays constant as I put more and more negative voltage. It's just the capacitance of the oxide. Okay? Now I'm getting to the point where I want to start to try to turn my device on. So I'm going to try to get the threshold voltage. Notice how the capacitance starts to dip down. That's because as you try to turn a MOSFET on, the first thing that happens before you get your channel to form is that you get depletion, right? When I get depletion, all the holes here are depleted out, and I end up with a dielectric here, which is the oxide, and a depleted region, which is also like a dielectric, right? It is depleted of all conductive charges. And so what I get, effectively, is something that looks like two capacitors in series, right? One capacitor being the oxide, the other capacitor being this semiconductor region, which is depleted. So I get two capacitors in series, which is lower capacitance. My capacitance dips down as my depletion region grows wider and wider. Here's my threshold voltage, 0 volts threshold voltage. When I get close to threshold voltage, all of a sudden my capacitance spikes back up very quickly. Why is that? Well, once you get close to threshold voltage and get above it, you get inversion where electrons show up here. If I have my charge here and charge here, then finally, once again, I've got my charges dropped only across the oxide, and so my capacitance goes up to the point where it's just that of the insulator. Hence why this is saying Ci, the insulator is the oxide, that's the capacitance I have here. And if I put more and more gate voltage, you get more electrons, but my capacitance stays constant because you always have the oxide there and the oxide's not changing. Has a given thickness, has a given dielectric thickness. There you go. So my capacitance goes from that of just the oxide in accumulation or inversion down to the point for depletion, where is it a series capacitance of the oxide and the depletion capacitance. And that's saying everything here as well. You should be able to know these three regions. Here, my depletion region is non-existent, so this is just like a simple metal insulator, metal capacitor, where it's metal insulator but semiconductor. Okay. Here, my depletion causes depletion capacitance to appear. It's in series, so depletion, the capacitance dips. And here, my depletion maximizes, but you have that inversion charge showing up on the oxide surface and makes it again look like a metal insulator, metal type capacitor. One thing I'll note is this is for low frequency. When you go into higher frequencies, this model changes a little bit, but that's a little bit beyond the scope of this introductory course. So at this point, you can do some last review when you're done with advanced MOSFETs. So when I switch, first question, what terms in my full threshold voltage equations invert in sign for PMOS? This is NMOS. Both of these are NMOS. If I switch this to PMOS, which of these four terms will invert, meaning they just flip in terms of their polarity? Second question is, which of these terms will shift? Meaning they don't change in polarity, they just change in magnitude, become greater or smaller, but they don't change in polarity. Here's a key question, and this was how we figured out how inverters worked. For this device I have here, what's the voltage out here in the P-type substrate? Remember, I'm only applying voltages out here externally to the source and drain. This is left floating, but I know what the voltage is based on the available voltages out here. So what would the voltage be? You should be able to figure that out for this device. How will the MOSFET capacitance change with gate voltage? So as I go anywhere from accumulation to depletion to inversion, how does that capacitance change? There are three factors and regions which we just showed on the previous slide. Last question, is the drain current versus gate voltage, which is called my transfer characteristic, is it linear or exponential? And what fundamental three-variable equation determines it and why? You should be able to figure out if it's linear and exponential based on two things. One, this fundamental three-variable equation, which is looking at charge across a capacitor, Q equals CV. The other way you know that it has to be linear is based on transconductance. So if you look back to that slide, you should be able to look at transconductance and know that has a linear relationship as well. The last thing I'll note is next time we will actually look at a layout in terms of when you integrate these things, and we'll be able to figure out also where you put the material systems and how you actually attach the metal lines top side looking down at a device like this.